Okay, so we just spent a little bit of time talking about the big picture on wind, like how much capacity we have globally. We talked a little bit about the physics of what makes the wind blow. We even talked a little bit about the equations of wind power. Now let's start to look at some of the zany ways that humans have come up with to turn that nature from energy into nature for our technologies. So what we're looking at right here is a top view of a technology where wind comes in here on the right side. You've got a screen, obviously, so that the blades on the right are not competing with the blades on the left, and there we go, spins. Another one where the one in A would be where you have predictable prevailing winds coming from one direction. Let's say you don't know, so you've sort of hedged your bets and put screens on all of the left-hand sides, if you will, or the counterclockwise sides, and allowed the wind to come in on the direction that you'd like it to spin. Obviously, you have to pick a side. I mean, there's really no reason why you would do the left or the right. You could take the mirror image of this, well, not the mirror image, but the upside down, well, put it in a mirror, like look from the back side of the page, if you will. It'll work the same way. This particular technology, I've never seen one of these, but you can imagine how it works. Each one of the blades are pinned at the edge, so as the wind comes in, this blade is facing inward and cannot move, and therefore the force of the wind hits it, spins it. Once you get up to 12 o'clock, that blade flips out due to circumferential force, stays out, and now it's sort of back and ready to take another load. Pretty ingenious, but probably kind of noisy too. Same deal here. In this one, yeah, it's not really clear what's driving. It's not really clear what's allowing each of these blades to articulate, but obviously they're doing so as they spin. You can imagine some kind of complicated gearing beneath this to allow the blades to vary their pitch as they spin. This is kind of an anemometer style. We would not usually use this for getting energy. We'd use it for measuring wind speed. And then another one where you've got, rather than cup shapes, you've kind of got these V shapes where the anemometer is going to have much less drag blowing in one direction than the other. This, from the back side, it's sort of slicing through the wind. From the front side, it's catching the wind. Okay, so there's a few. Here's even more. And these are broadly broken into the category, let me make this a little bit bigger, of horizontal axis turbines. So single blade, double blade, three blade, obviously the most popular, multi-bladed. Just looking at these two, what do you think might be the primary difference between the three blade and the multi in terms of its sort of startup speed and its torque and all that?
Multi-blade is going to take longer to start up.
Well, maybe. You might look at the multi-blade and say it's so heavy it's going to take longer. In general, though, these guys are going to operate with a smaller puff of wind, believe it or not, because there's just more stuff to hit. The other thing about the multi-bladed is they're going to have, in general, a higher torque, so you can think of them as like a low gear, but not as high of a RPMs. Whereas these guys are sort of a happy medium between the two. Single bladed, this guy can get whipping around really fast because it just doesn't have as much mass in general, but you're sort of missing all of this opportunity to catch some wind. Okay. Now, also in terms of horizontal, the upwind style, there's a little blade in the back that keeps it pointing upwind. Or in the case of the downwind, you forget the tail and just let the wind itself do the work of keeping the blades pointing in their direction where they're most effective. Okay. Here's another style. It looks like this guy actually has some kind of intake where the blades themselves are, have some airflow within them. I've never seen that type before. Might be some interesting research. Multi-rotor. So you've got the big investment in the towers. Just pack as many rotors on as you can. Why not? Instead of making big ones, these are in general sort of easier to fabricate. Here you've got one going counterclockwise, the other going clockwise. This is a crosswind, so it's still a vertical axis, and so the thing's still spinning about horizontal axis, so it's still sort of spinning with the top blowing and the bottom moving into the wind, if you will. This is kind of a squirrel cage, so the top is moving with the wind, the bottom is moving into the wind. In a diffuser, you got just relatively high velocity coming in, low velocity coming out, versus a concentrator, lower coming in, higher coming out, depending on your turbine type. So there, again, you're always looking at some type of equation like this. We already did the power equation for wind. Mechanically, for the actual physics of the energy in the wind itself, but now getting into the technology, power equals torque times angular velocity. So if you've got a turbine, the torque is tau, and that equals the force times the radius. Where's the radius? Well, that's how far it is from the root of the blade out to the end, and then the force is going to be a function of how hard the wind's blowing. The harder the wind's blowing, the more force you're going to see. And then the angular velocity is simply how fast it's spinning. So in the case of a linear system, the power would be more like this. Power equals some force times velocity. That's if you had like a car, nice little Dr. Seuss car there being pushed with some force at some velocity. In the case of a spinning technology, though, it's the torque times the angular velocity. The more torque, the more powerful. The faster it's spinning, the more powerful. Those are the only two variables to consider in terms of power coming out of your machine. So coming back to some of these guys, again, a lot of torque, not very high velocity. Not much torque, much higher velocity. In the case of the diffuser and the concentrator, depending on what your blade looked like, you might want something that's spins slow with a lot of torque, or spins fast with not much. That's the reason for all these wacky designs. Okay, so those are all horizontal axis, just meaning that the turbine is spinning like this. My finger's horizontal and the blade's always doing something like this regardless of the shape. Okay, and then the vertical axis. And you might say, well, gosh, aren't there three fundamental directions? Well, yeah, the vertical axis direction is really unique in that it's pointing up in the opposite direction of gravity. The horizontal is always perpendicular to gravity. And fundamentally, I mean, there's no magnets in here, so it doesn't really matter if you're north or south or east or west. The wind's just going to blow from whichever direction it does. Okay. So with the vertical axis, turbines. They're actually designed for places where you don't have a predictable wind coming, you don't have a trade wind coming from the same direction all the time. So they're designed to take wind from any direction, and thus the symmetry that you see. So multi-bladed S rotor, screen type, anemometer type. These are all drag-based, and they're also known as Savonius. And let me look that up for it. And Savonius turbine. I'm going to misspell it. There we go. So as you can see here, these are more or less acting like parachutes. They're based on drag. And if we look at the history here, Finnish engineer Sigurd Johan Savonius, 1922, is what this is named after because of his patents filed nearly 100 years ago. Okay. Now, these other designs are lift-based. And this is Darius. I'm going to misspell that too. Maybe, maybe not. Oh, actually I nailed that spelling. These are lift-based. So what's that mean? What's drag versus lift? We're going to look at that in a little more detail. But drag basically means the wind's blowing in this direction, my hand's a cup, and it's just being pulled along like a parachute. In the case of lift, and we'll see this in a little bit more detail, the wind comes in this direction, blows across one surface, creating low pressure, and more or less pulls it up. Now, in the case of these wind turbines we're looking at, there's no up, there's only out, and yeah, unfortunately, we can't. If we zoomed down in on this Darius blade, these blades themselves are like little wings of a aircraft, and so the draft or the lift is happening in a direction that, and we'll get into the physics, but there's no cup here on these things, and you might look at it like, how the heck does that thing even move? Well, in the same way you might look at an airplane, how the heck does the thing even fly? We'll get into it, but they're two fundamentally different things. So Savonius, Darius, and now combinations thereof. And I really want somebody to build me a winged rail vehicle so we can chase coal trains back and forth along the corridor. I think that'd just be a blast, wouldn't it? I mean, you've seen the windsurfers and the paragliders. I am yet to see a railroad wind-powered commuter, but that's what we got to do. Up and down the Bitterroot. I don't know, man. Nobody's on that thing. I think it's time to just build our own.
Hijack it.
Yeah. Okay. So here's going a little old school, traditional North European tower windmill. And you could hook up a variety of things to this, pumps, grinders. I'm sure you could even run a crude lathe off of it. What's mentioned though is the solidity of the blade. So this guy has a very low solidity. This one has a much higher solidity. Okay, and here's a bit more math for you. So I've already mentioned omega as the angular velocity. Now, if we look at the single blade spinning with some angular velocity omega, the units on this thing, omega is just measured in hertz. or 1 over seconds. It's the frequency. Another thing to keep in mind is that 1 RPM, that's normally how we measure things. That's how your car measures its rotations or revolutions inside your car engine. If we're going to convert this to a unit we can work with into hertz, it's actually going to become radians per second. So there are 2 pi radians in one circle, and there are 60 seconds in 1 minute. So that we end up with is 1 RPM is equal to 0.1047 radians per second. Now, why is this important? If we go back to the power equation, P equals tau omega. Let's take a look at that. P equals tau omega. What's a typical unit for torque? If you're talking about, like, if you're working on your car, you're going to measure that in foot-pounds, right? In the case of a turbine or any mechanical device, you're going to measure that in Newton meters, and then omega is going to be 1 over seconds. So let's just verify that the units work out. So if we take a Newton, we know that a Newton is a kilogram meter per second squared. And then we've got the meters there. That came straight out of torque times meters. And then we're left with omega, which is 1 over seconds. And that gives us kilograms meters squared per seconds cubed. Now, that definition, 1 kilogram meter squared per second cubed, that's 1 watt. That's the definition of the watt. So that's why it's critical that angular velocity be measured in hertz, which is radians per second, because radians doesn't have any dimension. It's just an angle. Okay. And now that allows us, if we know the angular velocity, we can then get the tip speed, u. I think that's given right here as u equals omega. Now I'm using a lowercase omega. The book uses an uppercase omega, but it's the same omega. Times r. The book uses a big R. I'm going to use a little r. It's okay. It's just the distance from the root of the blade out to the tip. Now, what does this tell us? Well, if r equals 0, we're standing right at the center of the blade and it's going 0. It's like, standing in the middle of your record player. You're getting pretty dizzy, but you're not going anywhere. The longer that blade gets, the faster it goes. So the bigger r gets, the faster u becomes. And this is just called the tip speed. That's just the tip speed. Oh, here we go. And this just after the equations here in box 7.2, it says dividing the tip speed u. So if we've got u divided by the undisturbed wind velocity, this is going to be v naught. The naught right there is more or less, going back up here, it's whatever the velocity is sort of out here, away from your turbine. So obviously, the wind's blowing that direction, the blade is going this direction, that's U. U divided by V, that's the tip speed ratio. I don't think it's actually given a number, maybe it is here. Oh, it's given a number lambda in the book, equals lambda. So let me just read this guy here. It says that a wind turbine of a particular design can operate over a range of tip speed ratios. So obviously, if it's not moving at all, it's zero. Once it gets up and running, it can only go so fast. But will usually operates with its best efficiency at a particular tip speed ratio. For example, when the velocity of its blade tips is a particular multiple of the wind velocity. This optimum tip speed ratio, lambda sub opt, is also denoted lambda sub max. With the corresponding efficiency, that's going to be the power coefficient. And it just goes on to say, optimum tip speed ratios for modern low solidity, so three-bladed turbine, low solidity turbines, range between about 6 and 20. So out at that tip, so if the wind's blowing at 20 miles per hour, that tip could be moving at 120 miles per hour. So I'll just say that's somewhere between 6 to 20. Torque is mentioned. I think we have a good idea of what that is. Now that we've sort of seen the schematics, gone over the definition of power and tip speed ratios, look at a few designs. And I'll just blow through these, and then we'll get into 7.4 after we review these designs. Okay, so there's high solidity. Here's a two-bladed. This is a 400. An MS 400, and I'm going to guess that means 400 kilowatts. WEG 400 kilowatts. That's typically what they're just rated in terms of power. Pretty big, not huge. Two blades, low solidity. Here's your three-blade. This is a Vestas V52, 850 kilowatts. Single blade, 600 kilowatts. These are all horizontal wind turbines. Horizontal axis wind turbines, or HAWT, as it mentions there in the book. Okay. Vertical axis. And again, these are lift-based, and I'll show you exactly what that means shortly. The drawback of a lot of these guys, relatively low solidity, sometimes they have to be jump-started. Because if you imagine the wind's just kind of blowing right through them, not doing anything, unless they catch that perfect angle. Think of yourself out in a sailboat. I mean, you don't want your sail straight into the wind. You don't want it perpendicular to wind. It's going to be somewhere in between the two. So unless that happens, you're going to maybe want to kickstart these guys. Here's one example of some of the early designs. And the reason for this thing, you might say, gosh, why did they make it so funny looking? Well, as this thing spins up, what you're getting is centrifugal force sort of blowing it apart. And so the blade, just the centrifugal force itself is going to cause it to take on that shape. So, why fight physics? Just make it that shape in the first place, allow it to do a little bit of bending, and not break. I've built these before, and they do get spinning fast enough that they can come right apart. So it happens. They will blow themselves apart. This guy, and so you can imagine, as this thing gets spinning, the top of this blade is going to want to bend out, so is the bottom, and it's going to want to take on that bow shape, more or less. And really, I mean, really, these are just airplane wings, kind of, they're just, it's a pair of airplanes chasing each other around in a circle, is about all it comes down to when you look at it. Yeah. 500 kilowatts. Okay, I think there's a couple more. And it sounds like these guys at the Open University in Milton have actually built a couple. And I think really all they're doing here is just using a little bit of simplicity. I mean, these aren't going to be the most energy efficient machines, but you can see they're simple and that there's like a single tower. They've got 3 guy wires holding them in place, a couple wires here to keep the thing from flying apart, and just, you know, a relatively simple structure. So maybe it's not the most efficient, bang for your buck, but they're keeping their costs down and building something that's kind of, you know, nice to look at and take some data from. Okay. I'll take a little pause on the recording, and we'll get into aerodynamics.